This is the video Introduction to Experiment 7, which is spectrophotometry of iron-containing solutions. Your goal in this experiment is to determine the amount of iron in an unknown liquid sample. This is going to be just like the calcium experiment, where your unknown will be given to you in a capped, numbered volumetric flask, and you're going to need to make it up to the mark before you analyze it. In this case, you're going to treat it exactly like your standard solutions, which you're going to make it up to the mark with other chemicals besides just water. We'll get there. The method you're going to use is you're going to take two different kinds of spectrophotometric measurements. First, you're going to make an absorption spectrum to find the wavelength of maximum absorption, the best wavelength to use on your instrument for your sample. You're going to use that wavelength then to make a calibration curve, which is a plot of concentration versus absorption, and then you're going to analyze your unknown and interpret the results of your unknown using that calibration curve. Your analyte is going to be iron, and your indicator is going to be a molecule called 1,10-phenanthroline, which is colorless in solution by itself. When it complexes to iron, it turns an orange-red color depending on the concentration. So since you haven't gotten there in lecture yet, a little bit of background. When you have an absorber in solution, a molecule that can absorb light, the amount of light that makes it through the sample is known as a transmittance. And this is this ratio, I over I naught. I naught is the amount of light, the number of photons that you shine on the sample. I is the amount that makes it through. And so transmittance is a ratio. On your instrument, it'll be expressed as a percentage. This is also, there's a definition of this thing that's 10 to the negative power of epsilon times L times C. Epsilon is the molar absorptivity, how good the molecule is at absorbing light at the given wavelength. L is the path length the light travels through the sample, and C is the concentration of the absorbing molecule. This is in the negative in the exponent because as the path length gets longer, or you get more absorbers, or the absorbers get better at absorbing, the transmittance goes down. The fraction of light that makes it through the sample goes down. What we generally use is not this ratio transmittance. We use an absolute quantity called absorbance. And this is found just by taking the negative log of the transmittance above. What this does is it gets rid of this 10 to the negative power dependence and just gives you a direct ratio. A equals epsilon times L times C. And what's important here is that now we have a linear relationship between absorbance and concentration of the absorber. If you plotted A versus C, you should get a straight line with slope epsilon times L and intercept of 0, which makes sense because no concentration of absorbers means nothing to absorb, which means no absorbance. The instrument that you're going to use to take your measurements is either going to look like this or like this. The difference is that the first one was an analog instrument, the second one was digital. There's no advantage to having either one. They're both just as good. You can get exactly the same measurements with each of them. Besides the iron standard solution, which you're going to have in a little vial at your bench, you're going to need these three chemicals. And it's very important to add these to your volumetric flask with your iron in the order that's specified in your lab manual. If you add them out of order, you'll get incomplete or no color development, which is bad because then the instrument won't have anything to see absorbing light. For the spectrophotometer, you're going to need these special test tubes. They're exactly the same size as the other test tubes we have in lab. The only difference is that they have this blue logo on them. That tells you that they're designed to work in the instrument to not absorb any light themselves. When you fill them up at least to the bottom of the blue circle so that you know that the light beam from the instrument is going only through liquid and not through air, which will change your measurements. When you make your calibration curve, so first of all, you're going to do your absorption spectrum with your most concentrated sample. In this picture, that's the one on the left. You're going to start with, and this corresponds to 10 milliliters of iron standard in the flask. You're going to start at 600 nanometers. You're going to work your way down to 400 nanometers in 20 nanometer steps. Find where the maximum absorption, the biggest numbers of absorption in that range are, and then go back and go over a smaller range in 5 nanometer increments, and then zero in on the maximum, and then a smaller range in 2 nanometer increments. This is going to help you find the wavelength of maximum absorption. What your instrument thinks is the wavelength where this iron 110 phenanthroline complex is best at absorbing light. This may not necessarily be the same as what you look up in the literature for what the wavelength should be for this complex. Once you've done that, you're going to analyze all of your standards at that wavelength and record their absorption. And so when you make up your 5 standards, this is what they should look like. You're not going to get 5 volumetric flasks. You're going to get 1. So make a solution, put it in a beaker, wait for the color to develop, and while you're waiting, make the next solution in the same flask. Make sure you rinse it out first, though. Okay, your data analysis is going to be different for the 2 different kinds of measurements that you do. For the absorption spectrum, it's pretty simple. Just find the biggest number. Find the wavelength of maximum absorption. On your data sheet, it's going to ask you to turn in this absorption spectrum. Make sure you turn in all the data points, the 20 nanometer, 5 nanometer, and 2 nanometer increment data points. For your calibration curve, finding the concentration of iron in your unknown. You're going to use that wavelength of maximum absorption. Find the absorbance of your 5 solutions at that wavelength in triplicate, and then measure the absorbance of your unknown solution. Using the absorbances of those 5 standard solutions, you're going to make a calibration curve, which should look something like this. I did this on 2 instruments, an analog and a digital, to show you that there really is no difference, because every year people complain, oh, I got the analog one. It doesn't matter. If you look at the 2 R-squared values, they're basically exactly the same. So these are your 5 calibration standards, and you're going to measure your unknown as well, and then put your unknown absorbance somewhere on this curve, then find the X value corresponding to that, which gives you your unknown iron concentration. So a reminder, because of all the snow days, you're going to do these measurements as a group. You're going to have 1 spectrophotometer for the bench, 1 set of test tubes, 1 set of flasks, 1 unknown, etc. All the data analysis, however, should be yours. Once you leave the lab, everything you turn in should be your own work, just like every week. So any plots you should make for yourself. Any explanation of those plots that goes on your data sheet needs to be your own work.